Okay, this is lesson 15. We're going to learn about series and parallel circuits in here, and specifically about resistors in series and parallel. So we're going to hopefully get you to learn, understand how to find the equivalent resistance for resistors connected in series and parallel. And so you'll probably recall that we did something similar for capacitors. We found their equivalent capacitance when they were connected in series and parallel. So we'll do the same thing for resistors. Um, so it's a little bit different how we do that, but similar but different. And then we'll also learn how to determine the current and voltage drop through electrical devices that are connected in series and parallel. So far we've been drawing a lot of pictures, very descriptive pictures of all these elements that we see in a circuit, like a capacitor and a battery and wires. But it's often inconvenient to have to do that all the time. So we actually have certain symbols that have been made up to represent basic elements in a circuit. And so these are some of the ones here that we'll use. And when we put them all together, when we draw how they all get set up to represent the circuit, we call this a schematic diagram. Okay, so a schematic diagram for this for this particular situation where we have a battery powering a capacitor, we would write for the battery, we would just have a long line and a short line. So sometimes you see that they have the one in this picture, it has a short line, a long, short, long, short. It's not always necessary to do that. Typically just one long line, one short line will represent a battery. And the long line represents a positive terminal, and the short end, the negative terminal. And then for a capacitor, we see they're just two parallel lines. Okay, sort of like for a parallel plate capacitor. Those parallel lines, and so it doesn't have to just be a parallel plate capacitor. It could be any capacitor too. Could be represented with that symbol. And then we would sort of try to, as neatly as we could, try to connect all these things with wires. And the wires is just pretty much a line. Okay, and so we try to kind of box things off as nicely as we can. And there's a lot of programs out there that you can do this with, um, and make really fancy schematic diagrams. So you don't have to do it by hand. Right. So let's try to make some schematic diagrams and see what's happening with the voltage drop and the currents here. So if we wanted to power up, use a battery to power a light bulb, okay, we would connect the light bulb with some wires. We may want to put a resistor in there as well. Depends on what we're trying to accomplish. Okay, and we connect them together, and we see connected like this that there's only one pathway for the current to flow, and so that means that the current is the same everywhere. Okay, but the voltage splits up. Okay, so each device, each element that's in the circuit has to share the voltage, the energy coming from the battery. And so sometimes we refer to the battery or whatever is powering the circuit as the source, because it's the source of energy. And then whatever's in the circuit that's using the energy, sometimes we'll refer to it as the load. Okay, So all materials have some resistance. We've learned even the wires have some resistance. Although for our purposes, we'll generally assume that they're ideal and not have to worry about that little bit of resistance that's lost compared to all the other things in the circuit. And so we could draw a schematic diagram of this situation. We can have the battery, the light bulb is sort of like this little loop, and you'll see that it's drawn slightly differently depending on the program you use, what book or manual you're looking at. Okay, the resistor is just kind of a zigzag line, and the wires back to the battery. And so this is a AA battery, so we could label this 1.5 volts here. And we know that the current's going to flow counterclockwise, going from the positive toward the negative. And so we know in this series type of circuit where there's only one pathway, the current is the same everywhere. Okay, so whatever the current is, it doesn't change anywhere along the path. But the voltage is different through different devices, different loads in the circuit. And so we see that in series circuits, the devices in the circuit have to share the total voltage. They get split up somehow. So let's say that the light bulb, let's say it uses 2/3 of the energy from the battery. Well, we would see then over this light bulb, there would be a voltage drop of 1 volt. Okay, so there would be 1.5 volts leaving the battery, right? It drops off. There's a voltage drop of 1 volt in the light bulb. That means leaving the light bulb heading toward the resistor, there's only half a volt left. And so we would see that resistor takes that last half a volt, and then the current brings back, there's no more voltage left to drop off. It heads back to the battery, picks up some more energy to drop off, and the cycle just continues over and over again. Okay, so we have here a light bulb. So two series circuits. The one on the left is powering just one light bulb, and the one on the right is powering 2 light bulbs. So you see here I have a potential difference of 120 volts. That's typically what comes out of your outlets in the United States anyway, is what they're set to. And so when you see 120 volts, you kind of think, okay, maybe this is, we're dealing with something that's plugged in here. Maybe it's not actually a battery, maybe it's some other power source. And so can you tell which light bulb experiences the most current flowing through it, and which one would be brighter? Okay, so remember that the current's the same everywhere in a series circuit, but the voltage splits up. Okay, and so in this first one, there's only one element using the voltage, so it takes that full 120 volts. Okay, whereas the 2 light bulbs in the circuit on the right, they have to split it up somehow. Okay, and it gets split up based on the amount of resistance in each bulb. And so since here we see that they're the same resistance, well then they'll evenly distribute the voltage. So each one will take 60 volts. Okay, and then we can use Ohm's law, V equals IR. We can use that to determine what's the current in each circuit. So then solve for I, it's just voltage divided by resistance. So in the circuit on the left, the voltage 120 divided by the resistance 20 ohms, well, that will give us 60 amps of current. Okay, and then we could find the current flowing through each bulb in the other circuit, V over R. This time each bulb, one bulb will use 60 volts, and they each have 20 ohms of resistance. So here the current is 30 amps. So we see that the current is higher when there's only one device in the circuit. So that means this bulb's going to be brighter, because it's getting all the voltage. These two, they'll be dimmer than the one in the circuit by itself, but these two will still be equally as bright because they are getting equal amounts of the voltage. So I'll show you a little demonstration of this. Okay, so here we'll look at this, and what we'll see here, there's 5 bulbs. There's 2 sets of 5 bulbs, so the ones on the right are connected in series. And so what we're going to do is we're going to turn the lights up, okay, when all 5 are lit up, and we see that they're equally as bright, same bulbs. The same bulb splitting up the voltage from the power supply, and there's a certain brightness. Okay, and what's also important to note is that if you take one bulb out of a series circuit, because there's only one pathway to follow, then everything goes out. There's a pathway that's been interrupted, and we used to see this a lot back when I was a kid. And my dad would put these colored lights up on the house during the winter time, and they'd all be hooked up in series. And so there would be the expression, if one bulb goes out, they all go out. And so we'd have to sit there taking out each bulb, putting a new one in, trying to figure out which was the bulb that had burned out. So it was a little inconvenient. They still do make them that way because it is cheaper. So if you go to like the dollar store, you might get some that are set up like that. But typically they're more all set up in parallel. That way, if one goes out, the rest of them still stay on. Okay, and now we'll hook it up just to 3 of the bulbs, and we'll see what the intensity looks like when 2 of the bulbs. All right, a lot brighter, right? All right, so now instead of 5 bulbs sharing 120 volts, because it's what we're plugged into a power supply into the wall that's giving 120 volts. So when 5 volts were sharing it, that 120 volts, they all got split up, right? 120 volts. Should be able to do this in my head, but 24. So they each got 24 volts. Okay, but now that only 2 of them have to share the 120 volts. Now they're each getting 60 volts, so they get brighter. They're still equally as bright because they're the same bulb. They have the same resistance, but they're brighter now. So now we'll have some resistors connected in series, 2 resistors specifically in series, and so with a light bulb, there are certain, you can see how the program I used to make this one, it uses a slightly different symbol. It's essentially the same, but it has like 3 loops instead of like the 1 loop that the book has. So there's some slight variation, but because the light bulb has resistance, we can consider it to be a resistor. But it just this particular resistor has the function of creating some light. And so we saw that the potential difference, the voltage, gets split up, right? And so the total, what we would say is maybe the total voltage, is just the sum. Okay, so oops, we could say that this is delta V TOT for total. Okay, and maybe this this resistor will get delta V1, and this resistor will get delta V2. Okay, and so if we were to put this in terms of Ohm's law, remember Ohm's law, V equals IR, then delta V total would be delta V1 plus delta V2. Okay? And like I said, in terms of Ohm's law, it would be I, the current, times the resistance of resistor 1. So we can call this resistor 1, we can call this resistor 2, R1, R2. R2 here. Okay, so the potential difference, or the voltage drop across the first resistor, is equivalent to the current times the resistance of resistor 1. And same thing for the voltage drop over the second resistor. Okay, I don't have to put I1 and I2 because we know that the current is the same everywhere in the series circuit. Okay, so we can also say, well, since I is the same, we can pull that out. We can factor it out, we say, right? And so the resistance, the total resistance through the circuit, okay, so between one end of the battery to the other, we could say then the total resistance of the circuit is just the sum of each of the resistors, okay? And that's what we call equivalent resistance. So the equivalent resistance is just the sum of the individual resistances of all the resistors in the circuit. Resistors, light bulbs, whatever. Okay, and so if we wanted to, we could create another circuit and say, well, I don't want to have two resistors. I just want to have one. Maybe I only have room for one on the breadboard, and so we could create another circuit with one resistor that had the equivalent resistance of these two. So that would be 40 ohms. Okay, and current still flows through it counterclockwise, but it would have the same effect. Okay, whether or not we have two 20 ohm resistors or one 40 ohm resistors, the current will still be the same in each circuit, right? Because we had the similar numbers before, okay, where we saw that in this circuit we had 30 amps flowing through. Okay, now if we do the current through our new circuit, V over R, then 120 volts over 40 ohms, well, we get 30 amps again running through there. Good. So in this circuit, we can actually measure. We can actually experimentally measure the current in a circuit by inserting in what we call an ammeter, as we do amps, right? And so what we would do in order to determine this is since we would just place it in series. Let's do this and place it in series. So this circuit here, and Okay, we put a little ammeter in there. Typically, we just have like a circle with an A, and that's our ammeter. Okay, we place it in series wherever we want to know the current, and in the series circuit, we could just place it anywhere, and it would be the same anywhere. And so the resistance of an ammeter is created so that it's small, so that it doesn't affect the measurement of the currents of what's going on inside the circuit. Right? If it had a lot of resistance, like even like 1 ohm in this 20 ohm with the circuit of 20 ohms, it could affect the measurement of what current's flowing through there. Okay, and so let's say the ammeter is reading 0.45 amps of current. Can we determine the potential difference or the EMF that's being provided by the source, the battery, or whatever the source is? Yeah, we know V equals IR. Okay, and then I is 0.45 amps. Resistance is 20 ohms. That means the voltage is 9 volts. Okay, so this may perhaps be a 9-volt battery that's being used here. Okay, so that's some series circuits. Now let's take a look at parallel circuits. So in a parallel circuit or in a series circuit, we saw that there was only one pathway for the current to flow through, whereas in a parallel circuit, there's multiple pathways. So we can have the same 3 items, the battery, the light bulb, and the resistor. We can connect them in series like we did before, or here we could connect them in parallel. Okay, create 2 separate pathways. And so here we see that the voltage is going to be the same everywhere, right? So kind of flipped from series circuits where the current was the same everywhere. But now it's the current that splits up, right? Whereas the current was the same in series circuits, but the voltage split up. Okay, so let's make a little schematic diagram of the situation. Okay, and so it's a 1.5 volt battery because that looks like a AA picture there. And so what we'll see is that the voltage drop is 1.5 across each one. Across each, the resistor gets 1.5 volts, the light bulb gets 1.5 volts. And then let's say that 3 amps are leaving the battery here. So we have 3 amps leaving the battery. Well, the current's going to split up. So if we measure that the resistor gets 1 amp, then that means 2 amps flows out of that junction and into this battery. Okay, and then 2 amps keeps going around until it gets to the next junction, okay, where again we now have come back to combine again to 3 amps. Okay, and then the voltage drop. We can see that they're when we draw it this way, it's nice because they're at the same level, and so we could really kind of visualize it as a drop. And so now the voltage, right, after it passes through the light bulb, right, and the battery, there's now 0 volts, and then 0 volts total goes back to the battery and picks up some more energy and goes through the cycle over and over again until the power is shut off. All right, so let's connect two resistors in parallel, like I have here. And so when they're connected in this way, we see there's more than one pathway for the current to flow after it leaves the battery. Okay, so we might say that there's a total current of I that leaves the battery, and maybe called the middle resistor, resistor 1, the one on the right, resistor 2, R1, R2. And then we'd see that the current I1 would flow down into resistor 1, the current I2 would flow down through resistor 2. Okay, so the voltage or the current will get split up, but the voltage will be the same. So each one of these resistors will get the full 120 volts. Okay, and so the total current then would just be I1 plus I2. Okay, and so then according to Ohm's law, this would just be there. I1 would, Ohm's law, right, is V equals IR. So I is V over R. And so I1 would have delta V over R1 plus delta V over R2. Okay. And we know that the delta V's, those are the same, right? So we can factor those out too, like we did before. Okay. And so then that's our current. Okay. So we can find then the equivalent resistance when resistors are connected in parallel. And so if we solve for R here, well, it's if we divide by I over 1 over R1 plus 1 over R2, delta V. We'll put the I over there. 1 over R1 plus 1 over R2 equals delta V over I. Okay. And V over I is R, right? When we solve for Ohm's law, R is voltage divided by current. So the equivalent resistance here we see is a little messy. And so, we're in the room, so I will take this and go. So basically, this whole thing here, right, or the bottom, the denominator is the R equivalent, right? So this is really saying 1 over R equivalent, right, equals 1 over R1 plus 1 over R2. Okay, a little weird, but we saw a similar thing happen with the capacitors when we found their equivalent capacitance. But we see now it's kind of flipped, right? And with capacitors, the equivalent resistance and the equivalent capacitance in parallel was just the sum of the capacitors. Okay, and in series it was the inverse of their sums. Now it's just kind of flipped here. It does the opposite thing. It's the same kind of pattern, but it just flips with resistance. So now in resistance, in series, the equivalent resistance is just the sum of the resistors. And now in parallel, it's the sum of their inverses. Okay, so we can, if we want, we can place, we could do the same thing. We can replace the two resistors with one resistor of equivalent resistance. Okay, so we wanted to do this, or we can, let's write just a kind of general expression for how to find equivalent resistance in parallel. And so we could likewise do the same thing. Find the equivalent resistance, put one resistor in there with that amount of resistance, and we'll get the same effect. Okay, so it just depends on what you're trying to do, um, what equipment, what electronic equipment you might have available at the time. Okay, and so we looked at ammeters was a way to measure way to measure currents. Well, to measure voltage or potential difference, we use something called a voltmeter, and voltmeters have to be placed in parallel. So we would do something like this. Have some wires. I have the voltmeter, right? Because the voltage drops over each electronic device in the circuit. So what in reality what this would actually look like is you would have your voltmeter, which nowadays is in something called a multimeter, where it has a combined voltmeter, ammeter, a meter to measure resistance, and some other things. And so it has two kind of prongs, and then you with wires connecting to it, and you just touch it around the device you want to find out, and then you can actually read what the voltage drop is across that device. All right, so let's try to kind of put it all together and see a more complex circuit. And so what would be the equivalent resistance of this circuit between points A on the top and B on the bottom? Well, we kind of got several things going on. We see that these two are in series. These two are in series. But the sets of these two that are in series are in parallel with each other too, right? And then we got another thing going on down here. So we'll just kind of take one branch at a time and simplify as best we can. So we know in series, the equivalent resistance is just a sum of each resistance. So for these two, 10 plus 40 is 50 ohms. And then the two on the right, we have 75 ohms. Okay, so now we essentially have a new circuit. I'll draw over here of okay, so now we have a new circuit that looks like this with a 50 ohm resistor here, 75 ohm resistor here, and a 10 ohm resistor here. Okay, and so now we could break it down some more. We could take these two in parallel, find out their equivalent resistance. 1 over Req equals 1 over 50 ohms plus 1 over 75 ohms. And so 1 over Req would be 0.03 repeated. And then solving for Req, I get 30 ohms. Okay, and now what we've done is we've condensed this circuit even more, so we can draw another circuit where we have the equivalent of a 30 ohm resistor there in series with a 10 ohm resistor here. And then 30 plus 10 is just 40 ohms. All right, so there's a few problems you could try out here with practicing equivalent resistance of series and parallel circuits, and practicing how the current and voltage drop work in each of these types of circuits, and a couple of extra example problems on the Moodle page. And so did you learn to find the equivalent resistance for resistors connected in series and parallel? So in series, the equivalent resistance is just the sum of the individual resistances of each resistor. In parallel, it was the inverses. Okay, so the same pattern as with capacitors, but flipped as far as what happens in series and what happens in parallel. And then we learned to determine the current and voltage drop through electrical devices in series and parallel circuits. So some important things to keep in mind as far as series, summed up here, is that the current's the same everywhere, but the voltage splits up. Okay, one pathway. Whereas with parallel, there's multiple pathways. Voltage is the same everywhere, and current splits up. Okay, so I know that when I was learning this, I had a really tough time trying to remember which was which. So I think it's a good idea to maybe keep this slide or a note or something somewhere that as you're doing these problems to help remind you what happens in which type of circuit. And then that's it for lesson 15.